Okay, so now, do you guys remember what was the topic last time? Just to, for all of us, I guess, to start with something, let's quickly review what was the last time on the agenda. Does anybody remember? Should I start? Okay, so we had particle on a ring, particle on a sphere, and that was our path to hydrogen atom, right? So that's the idea. So today we will go for the hydrogen atom, and the way these simpler problems helped us before, that was just from the, well, breaking down the problem, the total problem, into the parts that then we used to build up the full problem. Okay, now what we have here is the hydrogen atom, right? So let's, today we will go to the hydrogen atom. And when we say hydrogen atom, what will be, I guess, the topic is really a little bit even more than just a hydrogen atom. It could be any hydrogenic atom, right? So turns out that if you have a positive charge, no matter how large it is, and the negative, but one electron is a key, because when we go for two electrons, that is much harder, okay? And that is already not exactly solvable in general. Like helium case is not solvable, but hydrogen is solvable. And so here we have classical forces, potential. All this is just a classical physics of a Coulomb interaction. And there are a bunch of constants that we don't really go and dwell into much because they're constant. So you just clump them together. And the important ones probably is just the one important constant is Z. And then there is a sign, right? So Z is the charge of the nucleus that we have in the middle. So the higher the charge, the stronger the attractive force, right? And so you could think of this attractive force as like well for this electron to fall potentially. But we know that it won't fall because then the wave function of electron from the delocalized will be very, very strongly localized, and that's bad for kinetic energy. So one thing I strive to achieve in this course is that you will understand quantum some sort of in intuitive way, that it's actually have this balance. Oh, like when it comes to chemistry, especially balance between potential and kinetic energy. And the kinetic energy, the way to think about is how curvy the object is. So the more curvy or the stronger, the higher the second derivative, that usually is correlated with wiggles, then the higher the kinetic energy, right? So if you within the certain volume have a lots of wiggles, that's high kinetic energy. That's how in the wave function terms we think about kinetic energy. Of course, in classical physics, kinetic energy is all about how fast things are moving because it's this mv squared divided by 2, so the v is velocity. While in the quantum physics, it's just a function how wiggly it is because the kinetic energy is a second derivative. So okay, so that's what makes the thing stable. Mathematical description of hydrogenic atoms. We use fixed nuclear approximation. We fix the nucleus because they are heavy and we can do it. And we can go and um, actually correct this approximation later if they are sort of, if we need to correct for high precision. Sometimes we do, but not in this course. In this course, it's perfectly fine to have fixed nucleus, and the error that comes from that is, as we will see, really small. And then once we have a center, it's like a sun in our planet system. It's convenient to count everything from it and work in this so-called spherical system of coordinates, which is a little bit weird, but this is turns out to be useful thing to consider, because the algebra, even though initially complicated because of the differentiation in the curvilinear coordinates, but then at the end of the day, the results are much nicer in terms of the dependence of the operators on the variables. Okay. So this is the Schrödinger equation for the hydrogenic atom, right? So this, what we have here is the kinetic energy, potential energy, and then in the curvilinear coordinate system, we simply obtain the kinetic energy after all the transformations that you now can do. And if you can't, please let me know. We could discuss that. We could discuss also with TA, right? So either way is fine. But if we do all these tedious calculations on what the kinetic energy is in the curvilinear coordinate, this simple thing in Cartesian, which is sum of second derivatives in the curvilinear coordinates, or it's another. Curvilinear is more general term for spherical, polar, or any other coordinates, because they're nonlinear functions of x, y, z, right? So we get this expression, okay? And then the nice thing again about this expression, it has similar structure as before for the particle on the sphere, right? So what the structure is, if you look at this, let's see. This part, there's this part. It's just constant multiplied by operator. We can call it A of R, right? So that's operator A of R. There's nothing else here. It's just a nuclear core. Sorry, it's the coordinate of the electron with respect to nucleus, right? R. And it's the radius vector, right? So this one. That's the only thing that is in this part. And then we have another function of R here, which we saw is really inertia momentum, right? Inertia tensor, the 2m e r squared. So this is just a multiplicative function. You could just multiply by it any function. So it's a simple function, while here it's the differential operator. But both are, this is A of R and this is B of R. And then we have L squared. L squared is the angular momentum, and it depends on two other variables, theta and phi. And why this is like a nested dough situation, because effectively what we have is our operator that is in the same form as L square operator. And let me sort of write it down sort of so that you could see the similarity, right? So this complicated thing is A of R plus B of R times L squared, and this is theta phi, right? And the L squared itself, it looks like this, where it's a different A, but operator of theta, B operator of theta, and then LZ squared, which is operator of phi, right? So you see the repetition of this motif that we have operator of one variable plus the same variable operator multiplied by the product, right? And we could solve why this is helpful, because we saw we can solve these problems using a product state, right? So you could find that any state of L square, we call them, oh, they're actually here, right? So we call them these spherical harmonics. Here they just written as a large theta phi. They in turn, they actually are the products of theta and phi, because this has a product structure. And then the total function, because it's an eigenfunction of the same type of operator, it's the product of function of R times products of theta phi. So overall, why this is like a nested dough situation, because interestingly, it is not much harder than particle in the three-dimensional box, because in the particle in three-dimensional box, we know that we have eigenstates that are product of eigenstates for each individual dimension. So in this case, psi is r, and then here we have some, let's call it function of theta times g function of phi, right? So all our solutions for the hydrogen atom or hydrogenic atom, they look like this, product of these three functions, okay? And of course, this is not a particle in a three-dimensional box. There are some similarities, but there are also some differences. So what is the main difference? The main difference is that once you define this thing, this function, the function of phi, or we had it function of particle on the ring, LZ, which was phi operator. So once we define this function, then it turns out that function defines the f function. And once we have f and g function, that defines the r function. So in a particle in a three-dimensional box, all three functions are completely independent. You could choose them whichever way you want. But in the hydrogen atom, when you choose function of solution, right, that correspond to a particular function in phi, then that will define a set of solutions you can have in theta, and that will define the set of solutions you have in r. Now, from this maybe abstract terms, we could go to, well, real thing that you already know. And the real thing which you already know is there is one s functions, and there's two s functions, there are three s functions, but there are no 1p function or 1d function. There's only 2p or 3d. Why is that? The reason is exactly what I just said. It turns out that for the angular quantum number L, it cannot be lower than n minus 1. Okay, so you need to go to 2 in n in order to be able to have p. You cannot have p functions for the 1 n equals 1, right? And so that is a consequence of this relation, effectively, that in order to solve the total hydrogen problem, we first solve particle on the ring, phi dependence. Then we solve, that's the LZ states. Then LZ states help us to build L square states, and L square states help us to build the kinetic energy operator states and the hydrogen atom in total, because if you look at the difference between the T operator and the total hydrogen Hamiltonian, so then we know that the difference is only the 1 over r. That is in the Coulomb potential, so that could be absorbed with the A of r, right? So it's a function. It's an operator that depends on small r. Okay, any questions about this? This is the kind of a general structure. Okay, so let's move on. Equation for angle and r dependence. All right, so we already talked that L square, we know it's a spherical harmonics. We did them last time. And now we can solve, we just, we have them. So what we'll do is we present the total wave function as a product of now new r of r, big R of small r. Big R is just that's just a function, right, of a small r, radial variable. And we use spherical harmonics as another product. It's like product in the total function, theta phi, right? So this is a psi of r theta phi. And we put it, so we get this equation for the radial part because these guys are eigen functions for the L square, right? So that's what allows us to get rid of them by applying the operator, switching the operator to a number, and that number, lambda, in this case is h bar square L divided by L plus, multiplied by L plus 1. So this is appearing here, right where we had this 1 over 2 me r square L square, right? So the L square turned into a number because we acted on the eigenstate of L square, and we got ourselves the equation for the radial part. As you could see, that equation will depend on what function did we select for this angular part, right? So that effectively defined our constant, that defined what r, large r of small r, we will get as a solution. All right, so that's the equation. Again, equation is just one-dimensional. Doesn't mean that it's easy. In old days, people were solving it. In modern days, we don't, because, well, it still involves some complicated functions. And we just state the solution. But those who are interested, yeah, just be my guest. If you're interested, you could check how to solve the radial part of the hydrogen atom problem. And there are sources that explain how the big R's are obtained. Okay. Now we're going to be just looking at the solutions. So as in any eigenvalue problem, solutions are twofold, like eigenvalues, the energies given like this. So the interesting part is that they have a bunch of constants that are of not very big value for us. The constants that are important is z squared. So again, the higher the charge of the nucleus in the middle, right? So for hydrogen, of course, z is 1, but for if you make helium plus problem, that's gonna be z equals 2. And then if you make lithium 2 plus, that's still 1 electron problem, that's z equals 3, and so on. So the energy levels will depend on z, and they also, another is a more important aspect, it's this principal quantum number n enumerates the solutions, right? So its energy depends on 1 over n squared. So interesting dependence, because we can compare that with the other dependencies that we've seen before. So let's see, what other dependencies could you remember? Let's go by memory lane. So what are the problems we already solved so far? The ones that kind of we did the time independent Schrodinger equation. So if somebody asks you which time independent Schrodinger equation problems can you solve, you should name 4 or 5, the ones that we went through. Okay, let's try. Who can give me at least one besides, well, the hydrogen atom that we are solving now, and we're getting the, well, the value that is given here, right? So what was the first eigenvalue problem that we solved in this course? Or if you don't remember the first, tell me any problem where we have solution for this problem, solution being functions and eigenvalues.
Particle in a box.
Particle in the box, that's great, Kendrick. Particle in the box. What else? How was particle in the box, by the way? Energy was scaling with n, like what? Do you remember off the top of your head? Of course, the higher the n, the higher the energy, right? But how does it scale? Like n linearly, n quadratically? Just off the
I
top of your head.
I don't remember.
Okay, it was n squared. Well, this will be important for later. Okay, particle in the box. What was next? What was after particle in the box? Something with oscillations.
Harmonic oscillation.
Harmonic oscillations, harmonic oscillator. That was the second problem. Very, very, very accurate. And energy levels of harmonic oscillator. How did they scale with n?
With the sine function.
Sine function. So sine function, that's hard to make sense of. Here's why. We generally know that the larger the n, the larger the energy, right? But sine function is oscillating, so it cannot be correct, right? So just we enumerate in levels with n, they go up, right? So the higher the n, the higher the level. So the sine function goes like this, so it cannot be sine function. Well, the right answer here is energy is proportional to n because it's h omega n plus 1/2. So hydrogen atom is this hydrogen atom I will get to, but harmonic oscillator is the simplest spectrum of all because it was like this. Every level equidistant from every other. Well, they just kind of go like a ladder. Okay, so linearly with n. So as you could see that potential of particle in the box was like this, potential of the harmonic oscillator was like this. And now, well, there was some preparatory problems, but 1D potential that was different because particle on the ring, particle on the sphere, the potential was like a particle in the box. It's just a different topology or different geometry of the problem, right? But here in 1 over r dependence, that was the potential. So the box was like depicted here. This was our box. And it's different, right? So now it's not like this particle in the box, not like harmonic oscillator, where this is the distance. It's more like this, right? So it looks like this. And therefore, the spectrum is really different. It's now 1 over and the 2n squares, right? So with minus, of course, because still the larger the n, then the higher the energy, right? But it goes from minus 1/2, right? So goes from minus 1/2 in atomic units and keeps going, going up, up. And actually n goes to infinity. The energy becomes 0. What does that mean? Let's see if you remember our discussion before. What is physically will be the
It's the ground state.
ground state. Okay. Ground state is the state that is the lowest in energy, right? So how can this here be a ground state if I have lower states? Huh? So it cannot be, right? It's like saying, oh, this is a ground floor, but there are infinitely many floors below it, right? So no, it cannot be ground floor. It cannot be ground state. What is it? What is this states where n equals to infinity, right? And the energy equals to 0, right? So here it's minus 1/2. Here it's 0 energy. What does it mean, 0 energy? Let's see, because we talked about this last lecture. at length. Oh, actually more than once. But don't be discouraged that repetition is the key, right? So even if you don't remember, I will try to make you remember by saying the same thing over and over, trying to do it differently every time so that it maybe will stick in your memory and you will know it next time I'll ask. But okay, well, let's say this time zero of energy in any molecule or atom corresponds to one and only one thing. It is complete and utter disintegration of the molecule to electrons and nuclei, which flew millions of miles away from each other. Okay, so that is zero. Ground zero is all the particles scattered so that there is no interaction between them. Okay, so that's what zero is. In this case of hydrogen or hydrogenic atom, we have how many particles? See if you can count to two. There are two particles, right? So they are electron and nucleus. And the state of zero energy corresponds to electron and nuclear being as far away as possible, right? So that's just, there are no interactions. The electron is flying away. And that's why after zero, we have positive energies right here. And they correspond to kinetic energy of electron flying with the with the increasing speed somewhere where the nucleus really doesn't really interact with the electron anymore because electron flew away. Okay, so that's the spectrum of the hydrogen. You could have infinitely many levels here from 1 n equals 1 to n equals infinity, right? Infinitely many levels. 1s, 2p, we'll talk about this sp d thing. 1s, 2p, 3d, and so on. Those are the levels, infinitely many, that correspond to electron orbiting, classically speaking, orbiting around the nucleus. Once we get past this infinity, the electron now is free. It's not bounded anymore. And so we have unbounded spectrum, which goes from 0 to plus infinity, because there is no limit how fast the electron can travel. Well, of course, in our non-relativistic quantum mechanics, there is no limit. Of course, in real physics, where speed of light is the limit, then you need to add speed of light, and people know that. That's not Schrödinger equation, that's a Dirac's equation. So we're not getting to those speeds, but somewhere here, when we reach the speed of light, the energy now becomes again restricted because you cannot go faster than speed of light. And Schrödinger equation requires some modification, but these levels here, they stay the same because their electron is not moving faster than speed of light or in near to speed of light. Okay, any questions regarding this sort of picture and what it means? Because we have different potential, different dependence on n, and there are two types of levels. Discrete, where things are localized still near the nucleus, and continuum. This is a continuum, this is discrete. You see this discrete, there's a vacuum, there is a separation between those levels. Here, there is no separation. Electron could be this, well, essentially there is no kind of energy gap between these levels. They are dense. Okay, so what this means is no matter how close the two levels are, there is always level in between. Okay, that's what continuum means. All right, great. Let's move on. If there are no further questions, Bohr radius, this is historically important, yes, unit of length because it's related to the Bohr atom model, right? And it is atomic, it's taken as atomic unit of length. So one atomic unit of length is one Bohr. And as we will see, That is the expected position of the electron if electron occupies 1s orbital in hydrogenic atom, right? Or in hydrogen atom in this particular case. And it just incorporates a lot of various constants. This is the definition. All these constants, they go into the Bohr radius. And this is the kind of expression in terms of angstroms. Could read all about that. There's also, I guess, more details on the Wikipedia page on this Bohr radius. It's a kind of historically interesting, maybe, unit. But for us, it's just, okay, atomic unit of length. One atomic unit of length is this Bohr radius, called like that for historical reasons. And that's the story of it. Now, we go to the energies and see, let's see. So this is the energy. We could write these energies in atomic units, right? So that's where it's very convenient. And the whole thing, the whole prefactor here, right there. This one, this prefactor turns out to be Bohr radius squared in the denominator, mass of electron h bar, and all of them, h bar equals to mass of electron equals to Bohr radius equal to 1. Of course, these guys are all different units. This is the energy time, this is mass, this is length, right? So, but it's all at 1 atomic unit off, right? So it's like, if we were going into the C units, then, or SI, then they would be like different units, but in the atomic units, they all 1, and they're just the different physical dimensions. And so what this means is really that we have this prefactor equal to 1, and we can write in atomic units energies as simply this minus z squared divided by 2n squared. And the EH is atomic units. Okay. All right. So now there is also another historical constant, Rydberg constant, that is useful if you want to think about not just energy, but what in physics we care more than energies are energy transitions, right? Because we can only measure transitions between various energies, not energies absolutely. That's why we need to talk about absolute energies, we need to say, what is the zero state? And so technically, even when we talk about absolute energies, we're really talking about energy differences. Because we zero in our system of coordinate for the energy is all these scattered electrons and nuclei, and whatever is more stable will have negative energies. But you see, even though we will talk about their absolute energies, since they are counted from zero, we could also see this discussion as a difference of energies, not absolute energies. Now, when we talk about transitions between maybe ground state and excited states, now we're talking about transitions between different states. Then we like to think about frequencies, right? So frequencies of light that will promote these transitions. And in order to describe that, we have this Rydberg constant that is just convenient way of writing energy divided by hc, right? So h is in the not a reduced Planck constant, but a normal Planck constant. And so we have these two Rydberg constants that are convenient for bookkeeping the numbers, and they are defined slightly differently. And the difference between them is really, in the beginning, we assumed that the nucleus is static for solving the hydrogen problem. That was Born-Oppenheimer separation. And this effectively could be thought as an infinite mass of the nucleus. That's why the solution for the hydrogen atom, which is obtained using that, results in the Rydberg constant, which is R infinity. And the true Rydberg constant that doesn't have infinite mass of the nucleus have this reduced mass, which we saw in the problem of two bodies, harmonic oscillator, right? So any harmonic oscillator, you have M1, spin M2, and then you could always think of the two bodies as translation of center of mass and oscillations in between, right? So that's how the reduced mass appears. Now in hydrogen atom, turns out you could do exactly the same. So it's two-body problem. Just now there is no spin. There is a like this well, right? So the Coulomb well that attracts electron. And so, but still, there is a nucleus with a certain mass, which is high compared to electron mass, but still, well, it's a finite. And you could define the reduced mass, and that's what actually can be done to solve the electron nuclear problem more accurately without assuming kind of static nucleus. So then the whole problem, and we don't go into this, I think, in this course, the whole problem then is the nucleus and then electron, and they kind of, these two particles sort of split or represented as a center of mass that has reduced mass plus the coordinate, which is the difference between the center of mass coordinate minus the electronic coordinate. So it's this center of mass coordinate and the difference coordinate. Those are the two coordinates that you could solve the problem for, and you could do that. It's just a little bit more complicated, but that results in a different Rydberg constant, and it could be used, as you could see, the difference very small, which is another way to say that the difference between assuming the nucleus is static or nucleus is really moving for the electronic problem is not such a big deal. Okay, because we can. All right, let me skip this part and go to the hydrogen atom energies, because this is, again, from historical perspective, was a kind of significant event showing quantumness of hydrogen atom. What people found is that there are this series of energy or series of excitations that one can create in the hydrogen atom, right? So how are these created? Well, you start with initial state in some n, and then you end up in a different n because of the excitation. And if you vary the final n, here, then there will be series of excitations. And then if you vary the initial n, there will be series of excitations for different initial n. And people, when they didn't know yet the theory, they were just discovering different series of the excitations depending on the initial n. And those were called Lehman, Baumer, Paschen, and so on. All these scientists, they were discovering, and then eventually Bohr came and others, creators of the quantum mechanics, and they say, hey guys, all this is really just well, different parts of one formula. Okay, and even sometimes this formula, I think even before quantum mechanics was sort of numerically discovered, some people were just putting pieces together, realized that well, there is this formula that describes many of these series together, but they didn't have theory, right? So they had this formula. It's like the situation is a lot like a situation with say the nation that in South America, Maya, right? So that nation actually was quite advanced in predicting eclipses and all sort of astronomical events. How they were so advanced? They had numerical ways to do it very accurately, but they didn't have theory, right? So that actually would produce those numerical answers. So they didn't have really understanding of why these formulas work. So in our age of AI, sometimes you can uh, find numerically something that fits very well the phenomena, but if you don't have theory, you never know when is it gonna break or when is it gonna work, stuff like that. So it's important to have theory. We're not only about the numbers. And this is the one example where without the theory, yeah, these are just formulas, they can be derived, but they don't explain why the hydrogen spectrum is like this. In order to explain it, we need to formulate Schrödinger equation, we need to solve it, and that's a big deal because then it explains the transitions in this in this type of systems. Okay, so theory is important. That's the bottom line. Now, this is yet another ground state. It's about ground state energy. As I said, it's minus 1/2, easy to remember atomic units right here. And then in electron volts is another different system of units. Then you get 13.6, but 13.6 is harder to remember than minus 1/2. So I prefer atomic units when it comes to hydrogen atom because they skip all the constants. Okay, so here's type of a problem that one can try to solve on the exam or homework. We can calculate a wavelength of light emitted when an electron falls from the 100th orbit to 99 orbit, right? So it's a highly excited electron, which goes from 100 to 99 orbit of the helium plus atom. See, helium plus still has one electron and one nucleus, but Z part is not one like in hydrogen atom. Z part is 2 for the helium. Something to remember. Okay, report answer in centimeters. So we want energy difference that is translated into the frequency of light that will get emitted, right? Because when you have 100 level and goes to 99, the system goes like this, then it produces the light. And then the question is, what is the frequency of that light? So you need delta E, and then delta E is h mu, and the mu will be the frequency. So you need to divide delta E by h, and that's going to be frequency. You need just to formulate frequency in centimeters. How do you do that? Well, we have this formula, nice formula, lambda mu equals c. So we could use that to define lambda, which is c over mu. Right, so all that stuff we did, right? So, and we could go like that, or here is the example where we can use this Rydberg constant because the frequency is just this Rydberg constant, z square divided by n square. You put this Rydberg constant, it's already given you energies in centimeters or frequency in centimeters, and the math is relatively simple. You just do the difference between 100th level and 99th level. I guess this formula assumes we go between nth level to free system, right? And then that's why you need to kind of differentiate or subtract two frequencies, right? So to get the frequency of the light that comes, because we don't go from 99 or from 100 level to 0 energy free electron, we go from 100 to 99. Okay. Any questions regarding this procedure? All right, so let's continue. Okay, so we discussed quite thoroughly the frequencies, the energies. Now it's time to talk about functions, right? Because whenever we discuss eigenvalue problem, there are two components of solution: eigenvalues and eigenvectors or eigenfunctions. So here we go to the second part, eigenfunctions, and that's where you meet all your old friends, quantum numbers, right? Because we remember from general chemistry, so this is the solutions, N, L, M. Those are quantum numbers. N is a principal, angular, and projection, M, which is on the z-axis. And that's because N is used to enumerate the radial part. It depends, as you could see here, on L, and L was L square, angular momentum, and L square in its turn depends on M, which is LZ, angular momentum, right? So this is the progression. And turns out that their dependence is more from top down and defines how large the L can be, and L defines how large M can be. Right, so that's all we know from general chemistry. Hopefully it's imprinted in our memories now forever. Okay, that's common thing. And here the states where we have essentially convenient coordinate for the distance are divided by Bohr radius, right? So that's the radial part. And then we multiply the radial part by spherical harmonics Lm. So it's becoming more complicated once we go to the higher N, L, and M. But this is, yeah, these two first, at least, they don't have any angular dependence. For L equals 0, M equals 0, the angular dependence is constant, no dependence, right? And this is just the radial part. As you could see, one feature for all the radial parts everywhere, they are decaying exponentially with this raw value, or they decaying exponentially. It's the same as decaying exponentially with R. So for the atom, if you have a nucleus at 0, so then the electronic density decays exponentially with R. It's something to remember, right? So the only difference between all these states is that there is also polynomial function of R in front of this exponential. But that doesn't matter because, well, in long term, in long run, in long scale, it doesn't matter because any polynomial function will be suppressed by decaying exponential function, right? So any polynomial of R times exponential of R, so that goes to 0 when R goes to infinity. So the atom sort of essentially at some point we say there's no atom anymore, there's empty space, right? So because density is vanished. Okay, so then there are these known terms that usually people use for L equals 0, 1, 2, 3, 4, SPDFGH, letters. And we also could use contour surface plots for hydrogenic orbitals, because it's now we have 3 coordinates, and how do we really show function of 3 coordinates in, like, let's say the best situation, we have 3-dimensional space, right? So even though plots are all 2-dimensional, but with a little bit of art skills, we can show the 3-dimensional plots. But if you think about it, function of 3 dimensions requires 4 dimensions to plot, right? Because 3 coordinates for showing how function changes, And then there is a value of the function. That's the fourth coordinate. So there is no chance you can draw a three-dimensional function represented in a three-dimensional space. So that's why people came up with this nice trick. Let's look at contour of the surface for which the function has the same value. Okay, so that's the logic here. If let's say I want a contour plot of the function that has value 0.1, right? So here, of course, another always way to do the plots is you do the cuts. You do the one-dimensional cut, like here, the radial cut, then you do phi cut or theta cut. You do all these cuts, but then it's like you have different maps. How function depends at the particular value of frozen coordinates and some value of the one coordinate. And then it's like atlas. Essentially, you need to have all these maps together, and it's not convenient. But the contour plot is convenient, sort of gives you isosurface plots. For 1s, it's like spherical, and then for other say 2p orbitals, then they are of this shape, right? But of course, if you say, all right, give me a function contour plot, which will have a smaller value, what do you think will happen? It's like in Gauss view, you maybe already tried that, maybe not. But if you plot in orbitals for hydrogen atom or molecules, you could do this. And if you put the lower threshold, do you think your orbital will be bigger, the plot, or smaller? Let's see if you have an intuition about that. Oh, come on. So what are we plotting? The contour, right? So if the threshold is smaller, then function is decaying, so with the radius. And that means if you put the threshold smaller, then the function will be bigger, because at the larger radius, that threshold will be met, right? So that's very simple. The smaller threshold for this isospectral surfaces, the bigger the orbital will be. If you have larger threshold, then because the whole thing decays with the radius, and radius sort of comes from the center, it makes things bigger looking. So you'll get for the smaller threshold, you get bigger. For the larger threshold, you're gonna get smaller objects. Something to keep in mind. Okay, so one other last thing before the break. So we have real value 2p orbitals and the complex value 2p orbitals. What's the difference? Do you guys remember? Because I think we discussed this when we were talking about spherical harmonics, right? So you should remember that there are two symmetry operators. Let's see if you remember what are they. For the hydrogen atom or any hydrogenic atom, there are two symmetries at least. The operators that commute with Hamiltonian, what are they? The answer I'm looking for is a projection of angular momentum to one of the axes. We usually choose z, Lz, and L square. Those are the two symmetries. And if you solve for hydrogen atom and those symmetries, you get this states that are not real. They are complex functions. That's okay, because we care about absolute square as a probability density, right? So that's okay for the function to be complex. But if you want to plot something, the complexity of function becomes sort of a burden, because even with these isospectral plots, well, people still wanna have. Then it's like you have the two components, real and imaginary, and you then go for absolute value, which is the kind of combination of two components. So for the reasons that people want to have something real to plot, they decided, okay, well, we will like think about px and py instead of this solutions for angular momentum, which were p plus 1 and p minus 1. That's how the real valued 2p orbitals appear. All right, let's do a small break, and we will, yes, let's see. I think it's almost done. Yeah, so this was about the radial component for D and other 2p, D, those things that you could look at, and even F, look yourself, and then probability densities from the experimental snapshots are given here as well, so you could take a look. If you have any questions, let me know. So let's make a quick break, and then we'll continue to some last section on the radial behavior of the hydrogen atom. Okay. All right, let's continue. Okay, so really the last thing to consider about the radial dependence is how we can navigate in the questions of how much electron density we have within a certain radius shell. Okay, so that's what we're going to be considering, and this is really about, maybe if you want something very concrete, it's like a size of the atom, right? So if one wants to think of what's the size of the atom, then one way to define this could be, okay, find me the radius which encompasses the 99% of the density, electron density of a hydrogen atom. So makes sense. Of course, no matter what definition you choose, this 99% is completely arbitrary. You could say 99, you could say some other numbers or some other criteria on the where do you cut, essentially. But in order to calculate how much do we have inside a particular sphere, we need to integrate, right? And we need to integrate in this curvilinear or spherical coordinates. This is the quick review on how it's done. Of course, this is not to substitute the regular calculus, where this is done properly with all the theorems, but here I'll just show you a few basic ideas. And the main one, it's of course always easy to start with smaller dimensions, like a 2D case. And when we integrate in 2 dimensions, the usual, how do we do that? What's the integral in 2 dimensions? Is some function of 2 dimensions, x and y, and element of the area, ds, which is dx dy. And then this practically is, or from the theoretical point of view even, that it's this delta s multiplied by the function's values in this sum over I. So it's essentially the value of the function in the small squares multiplied by the size of the square. Okay, so that's what, and then what integral is the limit of this sum where delta s goes to 0, right? So you want to make sure that, of course, if your delta s goes to 0, the number of the squares become bigger. If you have some area which you want to integrate over, the number of squares become bigger, but the delta s becomes smaller, right? And if there is a limit, then there is an integral. So that's the existence of the integral criterion, that there is always a limit, no matter how small the delta s is. It converges to something. If it doesn't converge, then there's no integral. And most of the functions, they are, at least numerically, possible to integrate. There is a limit, right? Now, when we consider the same problem, but let's say the area is now described using some sort of coordinate system that is not rectangular but polar, right? So we have r and phi. Then, interestingly, we need to correct for some distortions. And the distortion is here that even though there is a d phi, that, well, the bigger the angle, the bigger the element of the area. But there is also, when we come to the radius, if the radius is small, close to the center, then the elements will be smaller than compared to far from the center. So it's not just dr, it's r times dr that makes the right scaling of the element of the surface, right, or the area. Because if we skip this r, then we will not calculate things properly. We will favor the elements out, let's say, close to the center, and we will then make the large elements which are far away from the center to count the same amount as the elements that are close to the center and which could be incredibly small. So this compensation is done. It seems like somewhat arbitrary. Why is it RDR, not the R square DR, for example, right? But in math, everything is, of course, done properly. This is just a result that one can obtain by looking at how do we go from the coordinate system, which is rectangular, to polar. And the proper way of doing this is using Jacobian. I don't want to go too much into all these theories of that calculus still need to properly teach you if you haven't. But the basic idea, as I said, we need to sort of compensate for the differences in curvilinear coordinates between the parts that are close to the center and the parts which are far from the center. And the compensation mechanism turns out to be related to the determinant of the transition matrix between, it's called Jacobian, between the polar and Cartesian coordinates, right? So that Jacobian turns out to be RDR, not R square dr. And then if we go to the spherical coordinates, there the situation is similar. There is a volume part, dx, dy, dz, and there is this volume part, but as a part of the shell. And that part of the shell could be smaller or bigger, depending on how close it's to the center, of course. Here, interestingly, this is R square because the Jacobian gives the R square in this particular case. And another feature is a sign of theta, which wasn't a part of the polar coordinate transition. This sign of theta, it's really coming from the fact that, well, the closer you are to the North Pole in this system, then your segment becomes smaller, okay? And R square here could be thought from the two parts. One from, well, I guess theta, another is from the R part. So, but properly speaking, it would be all just coming if you consider so-called Jacobian, and that is the coordinate transformation between the dr arcs, dr y, dr z, and here d phi, dx, d phi, dy, d phi, dz, and d theta, dx, d theta, dz. So if you do this determinant, calculating this derivatives, you will get these expressions. So that's how they appear. But for us, we could just use them. And when we do the integration in the spherical coordinate system, it's not going to be just dr, d phi, and d theta, but there is also this r square sine theta element of Jacobian, right? So the two infinitesimal elements of the electron density will be a function absolute square times element of the volume. But this element of the volume in the spherical coordinates is written like this. And this is going to be useful for us because we can then translate the electron density just by looking at the wave function absolute square and incorporate, essentially, we could integrate all the angular elements, all the angular coordinates, theta and phi, into one function of R that after we can, well, sort of know for sure that if this integral, we know for sure that if absolute square of psi dv is 1, right, because of the normalization condition, then this d quantity is going to be useful because it also has this normalization from 0 to infinity. So the only variable in D is variable that of the radial variable. And if you integrate it from 0 to infinity, because the radial variable is always positive, comes out of the center, goes to infinity, that's also 1, right? And that sort of shows how electron density behave as a function of r, but all other coordinates are integrated because in the definition of D. So that's why we call D the radial probability density. Okay, so if you want to know how much of the electron density you have between 0 and A, so that all you need is to just integrate D and L are dr between 0 and L, A, right? So that's a probability of finding electron which is radially between 0 and A. Okay, so that's why this quantity is very, very nice, useful, and it also incorporates all the Jacobian stuff. And here is some illustration how it behaves. This D function of R. When we put some functions that we have usually as an eigenfunctions for a hydrogen atom, right? So the radial part, spherical harmonics. Then we do this integration. Some part of this integration is very simple, actually. It's analytical because we have spherical harmonics, which are eigenfunctions of the L square. They are normalized. And so if you integrate them properly with theta and phi, they give you just 1 because they are spherical harmonics normalized. And all you need for this DNL of R is R squared times, well, R squared is a part of the Jacobian, and it's multiplied by the big R, which is the radial component. Okay, so this is a very simple formula for this probability density. And the difference between the probability density without this R square and with R square is that in the beginning, without R square, probability from the radial part of the eigenfunction, that just has the highest value and then decays exponentially, as we saw. But in the case where we have R square, it corrects for the fact that even though the function is large in the close to the center, but the element of the volume is small, right? So infinitesimally small if R close to 0. That's why the function always, this D function always has this dip in the beginning. So it's, again, if you look at the polynomial function multiplied by the exponential function has a limit going to constant when R goes to 0. But if polynomial function goes to 0, then you get 0 value. That's what is happening. Right, so this just some illustrations for the D of R, but later what we can do, sort of problems, is the radial components written for different functions. They are becoming increasingly complicated, but they always have the same structure. It's a polynomial function times the exponential, right? So and that polynomial part becomes higher and higher in degree, depending on the n, right? So the principal quantum number. And L, because as you could see, the more complicated parts are always when it's for higher S functions. So L equals 0, M equals larger L, then you get more oscillations, because this one is 3p and this one is 3d. The polynomial part is actually quite simple. Well, here it has more components for the S. And these are some pictures you could take a look at. Plots for the radial only when we change the principal quantum number and angular quantum number. And the same plots can be done for the D, contrasting them with R square, right? So again, you could see that the behavior close to the origin for the D function always starts with 0 because of this R square zeros it. Okay, and then there are nodes appearing because of the effectively principal quantum number and also the angular quantum number. 3s has more nodes, and 3d has no nodes, 3p has one node, and so on. Right? Any questions here? Right, so these are more examples, and this is the typical problem. Show that 1s electron is most likely to be found at the distance r equals 0. So that means Bohr radius from the nucleus, right? So that's given, 1s orbital is given. And the solution is how do we really find what's the distance that is the most probable? It's we want in this D function to find the maximum of it, right? So that's the most likely position on a radial coordinate where you can find the maximum of this D function with respect to R, right? So we find this D function, it's right here. And then the usual way of finding the maximum in calculus with one variable, you differentiate the function and you see what R would give you 0. And after differentiation, you have these 3 parts. And you could see that they are 0 if R is equal to 0 here, R needs to be infinite here, and R needs to be equal to A0, so that this one is 0. And of course, why do we have 3 positions? Well, because when we differentiate, we don't, it's a condition for extremum, not for the maximum, right? And so when we look at all these 3 points, extremum points, 2 of them will be minima, the first one and the third one, minima of the D, and the one in the middle is a maximum, right? You could check that. How do you check that? You could either look at the second derivative, or you could just plot the function, see that okay, so this or not even plotting, but stepping aside from the point that you found, where the function becomes smaller or it's growing. So that will show you if it's becoming smaller, then you're in the maximum. If it's growing, then you're in minimum, right? So the solution become R equals A0. So that's why Bohr radius could be thought physically as a distance where it's the most probable distance from the nucleus to find electron when electron is in 1s orbital. Even when electron is in 2s orbital, then the situation will be different, because if you look at the plot, what is 2s orbital? Yeah, so this is what we were considering 1s. So this maximum is Bohr radius. But in case of 2s, there are interestingly 2 maxima. You can really simply look at the functions and find those maxima. It's not that hard. Okay, conceptually. Now, this is about finding the maximum of the radial distributions. There is another quantity, which is expected radius, right? So one can think of what is the most probable radius in terms of the what if I measure the radius, where is it gonna be? And if I do it multiple times, so that's the expectation value of the operator R, and this is the formula. Naturally, you just average R with the D, and you could get the slightly different expression integrating by parts. Right, so and that corresponds to find the average distance between the electron and the nucleus, right? So average distance, not the most probable, but average. Mind the difference. And so this is a solution. Effectively, we look at this average and integrate the expression. There is a known integral that you can use, and it's a 3/2 of Bohr radius, not the Bohr radius, but 3/2 of Bohr radius. So that's those two things, maximum of the d and expected r, they are different. So don't confuse them. The language is important. If in exam you are not sure, you could double check, but make sure you are calculating the right formula, because derivatives of the d is highest probability of finding, and the expected value of r is, well, expected value of r. It's different. All right. Now, there are some integrals that usually appear in those problems when we look at the different d functions, right? And they can be all obtained integration by parts because they have polynomial and exponential function. So it shouldn't be a problem. If it is, let me know. And the only other thing that I wanted to highlight is that we talked about angular momentum in hydrogenic atom. We talked about LZ, L square being symmetries. And just this is a review of quantum numbers, N, L, M. Where do they come from? M from LZ, L from L square, and N is from the radial part, principal quantum number, right? But the story of hydrogen atom would be incomplete if we don't talk about electron spin, and that is internal angular momentum. So what this means is like there's a classical analogy that if the charged particle has a rotating sort of, well, classically again, rotating charge would interact with magnetic field, and that interaction would cause some changes in energy levels in quantum system. That's how people know that there is an angular momentum of for quantum particles. Now, it turns out that some systems, like here, this famous Stern-Gerlach experiment, which was 100 years ago, they did it on the silver atoms, and they knew already at that point that silver atoms, they have only s orbital states, so the angular momentum related to spherical motion, classical spherical motion of the electron on this s orbital, that's totally symmetric, and so it's a zero angular momentum, so it shouldn't be interacting with magnetic field. But when they did this experiment where they shoot silver atoms through the magnet, they found that magnet actually split the silver atoms, the beam, in two parts, and that simply would correspond physically to having angular momentum, and not just like angular momentum, not zero, but let's say 1, but actually 1/2. And that's how the spin was discovered, through this experiment where they realize, okay, there is some angular momentum that is non-zero, even though the quantum theory tells us that it should be zero. So what's going on here? They realize that, well, turns out that you need an extra quantum angular momentum, and it is, again, using the quantum analogy, it is almost like electron is something, some complex object where there are some rotating parts inside, right? But it's elementary particle, that's why it's sort of a contradiction. So there's no spinning charges in electron. It's usually in those stories where they want to illustrate quantum objects using classical intuition, they say, oh, it's almost like it's spinning, right? But in reality, it's just, it is what it is. It's just a property of the wave function, an additional angular momentum, which is called spin. And that's what every electron has. It's 1/2, and that's why we have spin up and down projections again. So the algebra of angular momentum is exactly the same as algebra of L. They are similar operators from algebraic point of view. It's just the normal angular momentum goes in integer values, and the spin of electron is 1/2 plus minus 1/2, or S itself is 1/2, but as Z goes minus 1/2 and plus 1/2 plus minus 1/2, right? And so we have also other components as Z, as X, as Y. But as in the case of hydrogen atom, if we want to solve problem for the Hamiltonian, we choose the symmetries of the Hamiltonian as square and as Z, not as X, as Y. The same way we choose L square and LZ, not LX, LY, right? And so that's what allows us to have this extra states alpha beta. They are orthogonal, and they have this they have definitions that alpha is the eigenstate of SZ with plus 1/2 and as beta with minus 1/2. That's all you probably seen many times in general chemistry, right? So on a quantum level, they are also orthogonal. So if you integrate the spin variables, you get between the same functions 1 and between different ones zeros. All right, so that's the last slide. If we look at the entire picture of the hydrogen atom, we'll have this many degenerate level, just crazy number, 2n square degenerate levels, depending on n, right? So the first level, n equals 1, has at least 2, up, spin down, 1s state. Then we go further, we have 2s, up and down, and then 2p, 3 levels. And note that they all have the same energy. In hydrogen atom, they all have the same energy because energy depends only on n. When we go to the multi-electron atoms, we still have SPDF sort of symmetries, but the sort of electronic levels, then the one electron functions are not eigenfunctions anymore. Things become more complicated, and there is a usually different, if we define somehow one electron orbitals, they are not of the same energy. So to S and to P, they could be of different energies. It's only in a hydrogen atom they are the same. Okay. All right. Any further questions? If not, think about don't forget to fill the evaluations, please, for this course, as your feedback is very important for us. Please do it before April 8. Now, there will be no lecture on Wednesday, but somewhere probably next week, we will have, I will try to post, before the next week, I'll try to post some example of final exam, right? And we will have tutorial, solving the problems, that sort of stuff, okay? It's probably gonna be next week, Wednesday, say. Okay, that we may, yeah, we'll try to accommodate as many people as possible. We'll coordinate online. Okay. All right, great. Then I guess see you next week. And unless you have questions, please stay and ask.